All right, let's dive right into this explainer and demystify a document that can literally make or break your construction site. I'm talking about the bar bending schedule, or BBS. If you've spent even a single day on site, you already know the absolute panic of hearing BBS not ready yet yelled across a slab while a concrete truck is just sitting there waiting. So today, we're going to master it.
Because honestly, this is the million-dollar question. What actually happens when the reinforcement cage doesn't fit the formwork? Well, if your detailing is off, you end up ordering the wrong steel, wasting material, and sitting there with cages that simply cannot be poured. A wrong BBS isn't just some tiny typo on a spreadsheet. It creates a domino effect: a wrong steel order, an incorrect bill, and a cage that literally will not fit.
So here's our roadmap for today. We'll start with what a BBS actually is, then cover the vocabulary of steel, the master cutting formula, how to calculate structural elements, and finally, how to avoid some seriously costly site mistakes.
All right, part 1. What is a BBS? Think of it as the ultimate bridge between design and site.
The crucial thing here is understanding exactly what this schedule represents to everyone involved. It serves as that ultimate bridge, connecting the structural designer's drawings, the billing engineer's purchase orders, and the bar bender's physical work right there on site. Think about it. The designer specifies diameters and spacing. The billing engineer needs the total tonnage to actually place the orders. And the fabricator, they need exact cutting lengths and shapes to turn a standard 12-meter stock bar into a ready-to-tie piece. And when you put it all together into a standard tabular document, it brilliantly illustrates the end goal. This standard format tells the fabricator exactly what to cut and bend, which ensures complete discipline on site. You absolutely need specific columns in an exact order, right? You need the bar mark to identify the piece, the diameter, the shape code, the cutting length in millimeters, the total numbers required, and finally the total weight. Anything less than that just invites mistakes. Moving on to part 2, the vocabulary of steel, specifically the constants from IS 2052 and IS 456. Look, before we touch any complex math, we have got to nail down this core vocabulary. Using guidelines like IS 2502 for shapes and IS 456 for lengths ensures your baseline detailing is mathematically sound. Basically, IS 2502 hands you the standard shape codes and bend allowances, while IS 456 dictates your required lengths, things like development and lap lengths. You literally cannot prepare a defensible BBS using only one of them. They have to work together. Now, keep the number 50 in mind, specifically 50 times the bar diameter, or 50D. This is the standard lap length for F500 steel in tension, and this is absolutely essential when a single 12-meter stock bar just can't reach the full span. Say you have a continuous column running up a multi-story building. You have to overlap those bars to transfer the stress, right? Forgetting this lap length is a classic, painful mistake that will leave your entire steel order short. Okay, next up, we really need to talk about bend deductions. Because whenever you bend a bar, you're actually stretching its outer edge. So you have to deduct specific allowances to make sure your final piece doesn't end up way too long. See, a straight bar's central line length is measured along the curve, but its outside dimension is measured along the straight extensions. If you bend a bar 90 degrees, it stretches, meaning you have to deduct 2 times the bar diameter. Get this wrong, and a cage with multiple bends is going to completely overshoot the formwork. No way around it. Which brings us to part 3, the master cutting formula, the core equation of it all. Honestly, this right here is the single most important concept of this entire explainer. If you strip away all the jargon, every single BBS calculation, whether you're looking at a straight bar, a crank, or a stirrup, comes down to one master expression. You sum up all the straight outside dimensions, add the length of any hooks at the ends, and then you subtract the deductions for every single bend. That's it. A junior engineer who truly understands this single formula will outpace someone who's just memorized 20 different shape-specific formulas without grasping the underlying logic every single time. All right, let's put it into practice in part 4, calculating structural elements, from stirrups to slabs. Let's apply this master key to something you see every day, the beam stirrup. When you follow these exact logical steps, what is normally a tedious manual task turns into this highly intuitive, error-free process. First off, you take the beam's width and depth and subtract the clear cover from all sides to get your outside dimensions. Then just sum those straight portions up. Next, add your seismic hooks, which are typically 10 times the diameter for safety. And finally, deduct those bends. For a standard rectangular stirrup, you're looking at deducting 3 90-degree bends and 2 135-degree bends. Easy. Okay, so once you've got your total cutting length, you multiply it by the number of bars, and then use a specific formula to find the total weight in kilograms per meter. That formula? The diameter squared divided by 162. This is the standard unit weight formula pulled right from IS 1786. So if we're using a 12 millimeter bar, that's 12 squared, which is 144, divided by 162. That gives you roughly 0.888 kilograms per meter. You just multiply that by your total length, and boom, you have your exact steel weight. For an isolated footing mesh, the process is incredibly similar. You're really just applying it to an X and Y grid to get the total length for your bottom bars. You start with your total footing length, subtract the clear cover from both sides, and then add your two 90-degree standee legs. These are often around 150 millimeters, which do the critical job of anchoring the mesh against lifting during the concrete pour. Just whatever you do not forget to subtract those two 90-degree bends at the corners. And what about a one-way slab? Well, alternate bottom bars are cranked near the supports, which requires a very specific diagonal addition. See, the crank rises through the available depth of the slab, going from the bottom cover up to the top cover. This diagonal portion actually adds length to the bar. To account for this mathematically, you use a constant of 0.42 times the effective depth of the crank. And yep, you just plug that addition right back into your master formula. Wrapping things up with part 5, avoiding costly site mistakes through Excel automation and solid quality control. To really protect your project's budget, you need to treat these common pitfalls as your ultimate QA/QC checklist before ever handing a schedule over to the bar fabricator. Seriously, forgetting bend deductions is the most frequent error, and it results in cages that are just physically too big. Missing development length at the supports? Well, it might not break the slab, but it will guarantee your steel order is short every single time, which leads to massive billing headaches. Always ensure you are using clear cover, not nominal cover, and for the love of all things structural, double-check your lap lengths. Now, let's talk efficiency. You can totally automate your Excel sheet using a simple if formula to distribute the total weight into the correct diameter column, which is going to save you hours of mind-numbing data entry. Basically, you type equals IF, the diameter in your reference cell is 12, output the cutting length, otherwise output 0. Then multiply that whole thing by your unit weight. It creates this beautifully dynamic sheet. If you suddenly need to change a bar diameter from 12 millimeters to 16 millimeters, the weight just instantly jumps to the correct column. It's a lifesaver. Following these principles and standards ensures your structural components are going to work together perfectly without under-reinforcing or wasting money buying excess steel. Getting the BBS right up front means the rest of the concreting day basically just takes care of itself. It's one of those quiet, behind-the-scenes skills, but honestly, it is exactly what distinguishes a reactive, stressed-out engineer from a highly effective one. So, keep that master formula in your back pocket, and you'll never have to guess the answer to this final question again. Is your site's steel order truly reflecting the structural drawings, or are you just paying for excess waste? By mastering the bar bending schedule, you are protecting the structure, the budget, and your professional reputation. Think about the project you're on right now. How much steel could you save tomorrow just by calculating your bend deductions correctly?